Kepler-11f Exoplanet Data Analysis by Matthew Herons. Kepler-11f was discovered using the transit method, which uses the dimming of the star. If the dimming is detected over a regular interval and lasts a fixed period of time, then it is very probable that the planet is orbiting the star. This is the data from NASA that we will later use to determine various things about Kepler-11f. First, we will examine Kepler's first law of planetary motion. Here we are able to see that Kepler-11f has an elliptical orbit with the Sun located at one of the ellipse's foci, and it is very close to circular with an eccentricity of 0.013. Next, we will examine Kepler's second law of planetary motion, which states when a planet travels in an orbit, an imaginary line connecting the planet and the Sun continually sweeps out the same area during the same time interval. Here we are able to see that the areas and time intervals are equal, so Kepler-11f will have a slightly greater velocity at the arc whose length is slightly greater. Kepler's third law of planetary motion states that the square of the period t of a planet's motion divided by the cube of the semi-major axis of the orbit equals the same constant for all known planets. Next, we will begin our data analysis for Kepler-11f. Kepler-11f has an inclination of 89.47 degrees, a mass of 1.1944 times 10 to the 25 kilograms, a radius of 1.586379 times 10 to the 7 meters, a density of 0.69 grams per centimeters cubed, and a temperature of 544 Kelvin. Kepler-11 has a mass of 1.911429 times 10 to the 30 kilograms and a radius of 7.416096136 times 10 to the 8 meters. First, we will analyze Kepler-11f's motion in terms of Newton's first law of motion, which states an object in motion tends to stay in motion at constant velocity, and an object at rest will tend to stay at rest unless acted upon by a net external force. Velocity is a vector quantity, which means it has a magnitude and a direction. Kepler-11f has a velocity that is tangent to the orbit, therefore it has a change in direction, and that means it has an acceleration. This acceleration always points to the center of the circle. There is a linear relationship between F net and mass, and the slope of this line is equal to acceleration. So F net is equal to MAR, where AR is equal to the radial acceleration. By using Newton's third law of motion, we know that the force of gravity that the star exerts on Kepler-11f is equal to the magnitude of the force of gravity that Kepler-11f exerts on its star. Next, we will investigate gravity. Gravity is the centripetal force that keeps Kepler-11f in circular motion. Gravity is equal to the gravitational constant times the mass of the planet times the mass of the Sun divided by the orbital radius squared. And the gravitational constant is equal to 6.673 times 10 to the negative 11. If we plug in the data from the NASA website into this equation, we are able to determine the force of gravity between the two objects, and this is equal to 1.089203707 times 10 to the 24 newtons. Using this value for the force of gravity, we can determine the radial acceleration, which is equal to 0.09 meters per second squared. We can use that same formula to determine the acceleration caused by gravity on Kepler-11f. So Fg is equal to mg. So if we put that in there, and this is for an object that is on the surface of the planet, we can cancel out the mass of the object, and then we get g is equal to the gravitational constant times the mass of the planet over the radius squared. If we plug the values from NASA into that equation, we get that the acceleration caused by gravity on Kepler-11f is equal to 3.16706.528 meters per second squared, which is much less than Earth's, which is 9.81 meters per second squared. We can do the same calculation for Kepler-11 and we get the acceleration caused by gravity on Kepler-11 would be 231.9148689 meters per second squared. To determine the velocity that Kepler-11f has to travel at in order to orbit its sun, we can use Newton's second law. We know that Newton's second law is F net is equal to ma, and in this case the F net is also equal to the force of gravity, and the radial acceleration is equal to v squared over r. And so plugging into our equations, the force of gravity is equal to the gravitational constant times the mass of Kepler-11f times the mass of its sun over the orbital radius squared, and that's equal to the mass of the planet times the radial acceleration. So then we'll plug in v squared over r for our radial acceleration and cancel out the variables on each side to get that the velocity is equal to the square root of the gravitational constant times the mass of the sun over the orbital radius. If we plug in the values from NASA into our equation, we can determine the velocity, which is equal to 59,609.15715 meters per second. To determine the period, which is the time it takes to complete one orbit, we can plug in 2 pi r over t into the velocity equation, and we get that the period is equal to 2 pi r times the square root of r over the gravitational constant times the mass of the sun. The value for the period was already provided by NASA and is equal to 4.034016 times 10 to the 6 seconds. Kepler-11f is uninhabitable due to its temperature and density, which is less than water, due to its hydrogen and helium atmosphere, which is comparable to Saturn's.